There are a variety of different types of mutants out there. One of the most common ones that we do look for are called auxotrophic mutants. Auxotrophic mutants have lost their ability to grow because they've lost their ability to produce a necessary growth factor. So it's usually looking at anabolism reactions, so something that's built up by the organism. If it can no longer build it, we've got to feed it. And so if we can give it all of its food it needs, then we don't have to worry about its growth patterns. But if we don't give it everything it needs, perhaps it might die off. So these are just really common ones because they're really easy to look for, but you do have to do some replica plating, some conditional plating. So here's plate 1. Plate 1 has all the supplement media needed. So we had to add histidine, add biotin for this particular organism. We grew a bunch of colonies. I don't know why they didn't label 9 and 10, but they labeled 8 colonies. And then they grew it on a plate that was deficient in biotin, still had the histidine. They grew it on another plate that was deficient in histidine, still had the biotin. And as it's denoted here, we lost a colony in each. These are now auxotrophic mutants. So 6 is no longer able to make its own biotin. So if you take biotin away, it can no longer grow. 2 is deficient in its ability to make histidine. So if you take away histidine, it can no longer grow. If we give them both supplements, they all can grow. It's a great way to screen for mutants. But you do have to make sure you do have a full complement media on top of everything else because, again, it's a little bit more challenging to look for things that are missing more so than things that are the addition of a factor. One of the most common auxotrophic tests that's ever done is the Ames test, and I put a video of that in your soft chalk lecture. This relies on histidine deficient salmonella. These salmonella cannot grow in the presence of histidine, but if you add mutagens to microorganisms, they have a high rate of reversion and a high rate of mutation. So we look for salmonella that have mutated to get back their histidine abilities, so their histidine synthesis abilities. If you have a lot of growth, that means there's a lot of mutation. That means that it's a pretty good chance that what you're looking at is a mutagen. Since all DNA is pretty similar, we can use this as a preliminary screen for cancer drugs. If something is carcinogenic, it has to be mutagenic. And if it's mutagenic, it's going to change DNA. This gives us a quick screen for mutagens, because if it doesn't change the DNA, it's not a mutagen, and therefore it can't be a carcinogen. If it is a mutagen, it doesn't necessarily mean it's carcinogen, it just means it has to be screened further. So here is the Salmonella Ames test. So we use a Salmonella strain that cannot produce its own histidine. We add some liver extract because liver generally tends to activate carcinogens. We add a possible mutagen, and we plate it. We plate it on media with minimal histidine to try to induce mutations. If you don't get much mutation, then it's probably not a mutagen. If you get a lot of mutations occurring, then that's possibly a mutagen, and it needs to be screened further as far as being a potential carcinogen. There's other types of mutations out there. There's catabolic mutations. So instead of anabolic mutations that are missing something required in biosynthesis, this means they can no longer use a particular substrate for growth. So if you take out any other sugar besides maltose, we can look for maltose deficient mutants. If you have other sugars in there, you can't confirm that it's a maltose deficient mutant. We can look at conditional lethal mutants. They only die under certain conditions. And I'm not talking antibiotics. Obviously, antibacterials are going to kill bacteria. But other conditions, like it may only die under UV light. So it might be missing part of its SOS repair mechanism. It may only die in a little bit higher solute concentration. It's losing its ability to regulate salts. But if you put it under normal conditions, it's fine. Temperature sensitive is another one that is kind of conditionally lethal. So temperature sensitive, there's a permissive temperature that'll grow it, and a non-permissive, either a lower temperature or higher temperature, that'll prevent the growth. One of the biggest ones we look for is antibiotic resistance, and that's because it is a real hot field right now. We've got a big problem with antibiotic resistance, and so we want to know as much as we can about antibiotic resistance. As we use antibiotics, we start to develop some resistant bacteria, and especially if people diminish their antibiotics by truncating the course of antibiotics, these resistant bacteria can now proliferate and become a greater percentage of the population. When they become a greater percentage of the population, they can definitely spread this gene to other bacteria. So we use a lot of media with antibiotics to screen for potential mutants that are growing in the presence of antibiotics. And we also use it a lot in selecting for organisms by using antibiotics as a selection marker.